Namaskar and welcome to my channel. This is my DC circuits of lecture part 3. We start this lecture first by defining the current density. First we understand about cross-sectional area. Here you can see in the figure this is the circular cross-sectional area, and in the next picture you can see rectangular cross-sectional area. With the concept of this cross-sectional area, we now defined the current density. Current density is simply represented by capital J, and current density is the vector, so we have a right arrowhead on the top of this. Current density simply means the current per unit cross-sectional area. The mathematical form is I by A, and here is the expression for current which we have discussed in the drift velocity, that this A and this A can be cancelled out, and finally we have the expression for current density. J equals VEN is our final expression for current density. There is some discussion about SI unit and dimensions. I hope you are already familiar with this expression. J is I by A, I is current, A is area. So finally we have this, and this is the dimension, which is always put inside the square bracket. A is one of the 7th fundamental unit, and m minus 2 is just a length minus 2. This is about the dimension of current density. Now we are going to discuss about some key points. So the first one is the discussion about the current density, which is a vector. I will discuss it later. Current density is a vector. Any physical quantity to be a vector, it must have magnitude, it must have direction, as well as it must obey vector algebra. So the current density itself has a magnitude, there is no doubt. It also has a direction, and it also obeys vector algebra. Remember this concept. The magnitude of the current density gives how charge flow at a point, and the direction of it indicates the flow of positive charge. First, here is the next key points. Here you can see in the figure, this is the cross section, right? This is the cross sectional area of a conductor. I just have taken only the cross sectional area, and this is suppose here a conductor like this. So inside the conductor the current is flowing this way, that means in this way, and here is the cross sectional which is supposed in the orientation like this, and in this case the direction of cross-sectional area is this one, which is represented by the unit vector. It gives the direction of cross-sectional. We know any elementary area is itself a vector, because the direction of that cross-sectional area is given by the perpendicular drawn to the surface. So here is the same case that you can see here, and theta is the angle between the direction of flow of current and the direction of cross section. The magnitude of this cross section along the direction of current is given by the projection of A along I, which is a cos theta, that we have discussed previously in the vector chapter. I guess you have studied and you understand this concept. So under the cross multiplication, I have this expression I equals J cos theta, and this expression finally reduced into this form J dot A, because simply it is simply a dot product. So J dot A means J cos theta. So we have seen from this expression here that I is a scalar because I has become the dot product between two vectors, vector J and vector A, and J is a vector. J means the current density, and A is the vector which is the small elementary cross-sectional area. This is the figure almost about the concept which I have discussed here, and this is also about this, right? If theta is 0, and then we simply have a expression for current density is simply I by A. This is related to this figure because here is I, here is A, the angle between them is 0. But in this case, I is here and area of cross section is here, so there is some angle theta. So in this case the J is defined like this, J equals I by A cos theta. So it's simple. I hope you understand this. Now we move on to the next point. So you can see here in the slide, here is the simple expression which is a general expression that is extremely used in the kinematics. This expression valid only for constant accelerations, and it is simply the straight line motion. That means it is valid only for the straight line motion with constant accelerations. This general equation is also valid in case of the free electron inside the conductor, because inside the conductor, when we apply the external electric field, this electron experiences the electric force, and because of that electric force it experiences an acceleration in accordance with Newton's second law of motions. Because in Newton's second law of motions, if any particles experience force, it undergoes some accelerations. The same case happens in case of electron inside the conductor under the effect of external electric field. So here U is 0 because if there is no external electric field, the free electron is supposed to be at rest. So after applying the electric field, it undergoes some accelerations. So this expression really valid for electron as well. A means F by m, T means time. The time is the relaxation time, and F is the force which is the electric force experienced by the electron under the effect of external electric field, and m is the mass of the electron. It is relaxation time remains the same here, and here the negative sign indicates that the electrons get drifted, means shifted opposite to the applied electric field, which we have already discussed in the previous lecture. Electron has a negative charge, and because of this it is always attracted towards the positive end of the conductor. Of course, the electric field in that conductor will be in the opposite direction of the flow of electron. That means always directed towards the negative end of the conductor. Only the key points here that you should remember is the direction of electric field and the flow of electron is exactly opposite. So from these expressions we have seen drift velocity proportional to electric field and also proportional to relaxation time. And this is also further split into this E equals B by L. B is the potential difference, L is the length of the conductor. That means the distance between positive and negative end. So from these expressions we have drawn a conclusion that BD is independent of the cross-sectional area A only for that conductor which is uniform. Uniform means in the sense of constant resistance. If that conductor is not uniform, then obviously the drift velocity depends upon the cross-sectional area. Remember this concept, and which is important for us. Here you can see a points that we have to remember. Here in some books the average velocity has been calculated by taking initial and final velocities of free electron. So this expression is totally wrong, because we cannot take this one as the case like this, because drift velocity is simply the average of drift velocity of large number of electrons at same instant. You cannot take average velocity from two instants as we have done in the average velocity formula. The same process is not valid here. In case of electron, we have to take the average velocity of the large number of electrons at the same point. Means we just have the single value of average velocity that represents the velocity of whole electrons at a time. So the final formula must be like this. Here is no 2, as you have seen here. There is no 2, just we have a minus E tau by m. Alright, so you so remember this. Next we have a fourth point. First we try to understand the collision time here, which is the time taken by the free electron between two successive collision. Two successive collision means this is the first, this is the second. If electron collides and then collides, this is the two successive collision. This is first collision, this is two collision. So the time interval here is the collision time taken by the electron between two successive collisions. Then we have to understand the relaxation time. So the relaxation time simply means, suppose we have this man which is standing out here. He needs to complete 100-meter distance, no matter how much time does he take. If this man runs through 100 meter and at the end of this 100 meter he is not come at rest exactly, but he slows down his velocity, and finally he becomes at rest, right? This is the first mean position. This is the first equilibrium positions. Finally he has come to the equilibrium positions, and in this interval he is running out, but just at the end of 100 meter he is not finally at rest. He has to take some time before coming to rest. He is doing relax at this period. He is doing relax at this period. So the time what he has taken in this interval is, in this case, is just the relaxation time. So relaxation time simply means the time taken to be relaxed. So the simple definition is here. It is the time taken by the electron to reach the equilibrium position from the distributed position in the presence of electric field. The simplest definition is here. It is the average time that has elapsed, that has taken, that has passed, that has used, right? It is the average time that has taken since means this point. Each electron has suffered its last collision. Last collision means here becomes the last collisions, because suppose here is a number of collisions here, and this one is the last collisions, you can suppose, with the ion or atom of the conductor while drifting towards the positive end of the conductor under the influence of electric field. So relaxation time simply means the time taken, simply means the average time that has elapsed since each electron suffered its last collision. That means the time taken to be relaxed. That means the time taken by the electron after its last collision, finally to become at rest. So this time is the relaxation time, just the time taken in this interval from the final end of 100 meter. So you can compare this example and think over for the electron, so that you can easily understand the definition of relaxation time. It's simply the average time that has taken since each electron has suffered its last collision. This is the relaxation time. And here is the graph, which is relaxation time versus electric field. So this graph just shows that the relaxation time decreases exponentially. We don't need to explain this graph in details, just relaxation time decreases exponentially, and the relaxation time for the electron is of the order of 10 to the power minus 14 seconds. Just remember. Now next move on to another slide. First we try to understand the mean free path. Mean free path means average distance, that is the distance traveled by moving particle, in our case electron. So the average distance traveled by the electron between successive collisions. Average distance traveled by the electron between successive collisions. So here is the number of successive collisions that you can see here. This is first, second, third, and so on. If we add all the distance and multiply by the number of them, then we will finally get a single value of the distance This will be the distance between only two successive collisions. So this is of course average distance, and this average distance is called mean free path, right? This is the formula for the estimation of mean free path. Here is the distance, here is the volume, and here is the number of molecule per unit volume. This volume cancels out, and in the denominator we have only the number, in the numerator we have a distance. So the distance upon number of collisions only gives the average distance, and which is the mean free path. This is the general formula for the motion of the particle in a straight line, and so it is compared with this formula, where S is the lambda means mean free path, U is the root mean square velocity of the electron, T is the relaxation time. So from this expression we have the relaxation time, that is lambda by P RMS. I hope you understand this. Now next move on to another slide. Here is the basic points that we have to remember. The drift velocity of the free electron is of the order of 10 to the power minus 4 meter per second. This velocity is very small, and this is the RMS velocity of electron, which is of the order of 10 to the power 5 meter per second. And this is the relaxation time, which is 10 to the power minus 14 meter per second. And the order of propagation of current is almost about the velocity of light, which is 3 into 10 to the power 8 meter per second. So remember all this value. Now we have come to explain the numericals. I'm not going to describe these numericals details in here, because I have a separate video for you to take it easy to understand. So you have to follow my next video, and here is the next one. It is also described separately in the next video, and these are the questions for homework, so I'm not going to discuss in details here. Just you have to complete this out, and you can submit the answer of them in my Facebook page. The name of that is 10+2 Hyperphysics Discussion Forum. You can submit the answer of all these questions. I will check that. I will check if you comment, or you have to follow me on YouTube. I will separately describe them in the next videos. Alright, so this is our last description. I hope you understand better. And this is a famous quotations. The essence of science: ask an impertinent questions, and you are on the way to a pertinent answer. Did you enjoy my class? Yes or no? Please leave your valuable suggestion so that I will be better for you all in the next video. Your suggestions will be highly appreciated. Thanks for watching.